Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about the operational amplifier, so let's get started. Alright, so let's talk about the operational amplifier. And what I did here is I drew one, the symbol for an operational amplifier. Let's copy that one. Let's move it down here. Alright, so that's what we're going to use, alright? So this is the symbol for an operational amplifier. So we have two inputs and an output. The positive input, the term for that is called the non-inverting input. And the negative side, that's termed the inverting input. The output is simply your output. Alright? Now, how this thing works is that with your non-inverting input, if your positive input has a higher voltage, I'm going to put a little V, than your negative input, then your output is going to go up. Got it? If your non-inverting input is below, has a lower voltage, I should say, then your inverting input, or your minus, then your output is going to saturate low. So if you think about it, using common sense, if your plus is higher than your minus, it's going to go high. If the plus input is below your minus, it's going to go low. Alright? That's one way to remember it. So in a nutshell, that's it. But let's talk more about this amplifier, because we kind of jumped right into its operation. But I want to give you some more information about this, alright? So I'm just going to move this over here for you. So if we look at the characteristics of an amplifier, what do you think if we have an ideal amplifier versus an actual amplifier? Let's look at three characteristics. Input resistance, or R, between plus and minus. Ideally, that would be very, very high. Infinite for ideal. But actual is just going to be very, very high. Alright? If we look at your output resistance or output impedance, your output impedance is going to be, for the ideal case, 0. But in actual, it's just going to be very, very low. Alright? And one last thing, let's talk about the gain. So by the way, this is in ohms. This is in ohms. 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 Now AV, or gain, is unitless. Ideally, the gain of an amplifier is going to be infinite, right? Infinite gain. But in actuality, it's just very, very high. 100,000 maybe a little more. So, the actual op amp. Is it as good as the ideal? Obviously not. But it's good enough to do a lot of great things with it. Okay, it's a very, very useful component in many circuits. All right. So let's look at something else here. So we talked about the input, the non-inverting and the inverting input and the output. And we talked about its functionality here, right? Let me move this here. Move it out of the way. Now, the one thing I didn't draw here, which I'm going to draw now, are how you power the amplifier and how that affects your output. When you have an amplifier, you're also going to have two other inputs. You're going to have your positive voltage input and your negative voltage input. I just call this V plus and V minus. Now, suppose in the spec sheet for the operational amplifier, that's where all this comes from. Suppose we say, all right, let's call this plus 15 volts, all right? And let's call this one minus 15 volts. Got it? So the first thing you need to understand, if we have a gain that's, say, 100,000 or so, a very small difference in these voltages is what it's going to amplify. So if you have two signals coming in and there's a little bit of difference between them, now what difference does it mean? You're going to take that difference, whatever it is, multiply it times 100,000, and that's going to give you your volts coming out. All right? So if you have a millivolt difference between these, which is 1/1000th of a volt, and you multiply that times 100,000, your output's going to be 100 volts. Now obviously this amplifier cannot output 100 volts. It's only being given plus 15 volts and minus 15 volts. So what's it going to do? It's going to saturate. And it's going to saturate if the non-inverting input voltage is above the inverting voltage. It's going to saturate high, right? So, and it's going to saturate to a level below your power here, your 15 volts. So usually it's around a volt or so. It depends. You could measure. You're going to measure it probably in labs you have. But I'm just going to call this plus 14 volts. Similarly, if the difference, if your non-inverting input is below your inverting input voltage, by say a millivolt, it's going to saturate low. And the level where it's going to saturate is going to be around 14 volts or so. All right, so it's going to approach these voltages but not quite get there. All right? But remember, your gain of these amplifiers, these operational amplifiers, sometimes termed differential amplifiers, that's the term some people use, because it amplifies the difference of these inputs. The gain is very, very high. So there's a term used called open loop. And what that means, open loop means that the output of the amplifier is not fed back to one of the inputs. Okay? So usually if you're using these in open loop mode, you're just using it as a comparator. And the comparator basically gives you a high output voltage if your non-inverting input is above your inverting input, or it gives you a low voltage, obviously, if your non-inverting input voltage is below your input voltage, your inverting voltage, I'm sorry. All right? All right, see you soon. All right, so now let's talk about something called common mode. Now, if you have three characteristics to think about of the input signals, let's just think what they would be. So the first one would be the frequency. You can write down, sorry, there it is, frequency. What would be the next one? You want to have the same frequency. You probably want to have the same amplitude, right? That's an E there. And then the third thing is you're going to want to have the same phase. These are three characteristics of input signals, right? So if you have an input signal coming into your non-inverting input that looks like that, and you have another signal that's coming into your non-inverting input that looks like this, basically it's the same frequency, the same amplitude, and the same phase, which means they're directly in phase, right? Think about it. Now, the operational amplifier amplifies differences. There are no differences in these signals at any time, right? Theoretically. So your output would be 0 volts, right? So let me just state that again. If you have two signals coming into an operational amplifier, one signal at the non-inverting input, one signal at the inverting input, and they have the same frequency, they have the same amplitude, and the same phase, which means they're in phase, okay? Then the output of this operational amplifier would simply be 0, all right? There is a specification, and the specification has the 4 letters called CMRR. It stands for Common Mode Rejection Ratio. Basically, you want to have the common mode amplification very low, while you want to have the open loop gain of your amplifier very high, right? So what they do is they take a ratio between these two. So your common mode, it's going to be your gain open loop divided by your gain of your common mode, right? So remember, your common mode amplification is how much it amplifies something that's a signal that's in phase, same frequency, same phase, and same amplitude, right? It should be 0 volts. Sometimes it's not. And your open loop gain. Now this is going to be where your signal is. This generally is going to be where your noise is, right? So you want to have your signal amplified much more than you would any noise, all right? Generally this noise can come from a variety of sources, but it's radiated energy, and it sometimes comes from 60 hertz power that comes out of your lights, your sockets in your home or in your lab where you're at. It could be other things. But this ratio sometimes is listed in decibels. So it's going to be common mode rejection ratio is going to equal 20 log open loop gain divided by common mode. Alright? Now, this is an important parameter, and if you're building a circuit that's for low noise applications, you're obviously going to want to pay attention to this, because you want to make sure that your signal is amplified and not your noise. All right. All right, everyone. Thank you. I'll see you soon. All right, everybody. I want to talk about another operational amplifier characteristic called slew rate. Basically, the slew rate is defined as the rate of change of the output voltage compared to a step change in the input voltage. So let me explain. If you have your inverting input grounded and you have your non-inverting input with a signal that is ground initially, suppose that's 0 volts, and then it has a step function change. I don't know, suppose it goes say to 1 volt, just for example. All right, your output, what's your output going to do? Well, your output is obviously going to start out like this, and then it's going to jump up as well, right? But let's expand this part. Really, it's not instantaneous, okay? So if we write that again, this is actually going to look, it's here, and it's going to come up like this to another level, right? So this is your V out, right? So what we're interested in between these 2 points, right, that's your delta T, your change in time. We're interested in that time, and we're also interested in this voltage right here, change in voltage. So your slew rate is going to equal your change in voltage over your change in time, right? Generally, this is in volts per microsecond, and this micro means it stands for 10 to the minus 6, or 1/1,000,000th of a second, okay? Alright, so that's what your slew rate stands for. Now, I want to give you a drawing here because most discussions in textbooks use this kind of drawing when they talk about slew rate. At least those textbooks that I've seen, alright? So, for example, if this is your V out, that's V out, and this is your time. And suppose that your V initial, I'm going to call it V initial right here, is at this point, and then at some point you have that step function comes in, and then it's going to start changing. It's going to start rising. It's going to reach its voltage, its other voltage, whatever it may be, and then it's going to flatten out. All right. So your delta T that you're interested in is right here. That's your delta T. All right. Your change in voltage, suppose this is your final voltage over here, is going to be this value. All right. Delta V. Let's call this V final. Okay. All right. So if you look at your delta voltage divided by your change in time, that's going to be, what's it going to be? It's going to be V final minus V initial divided by, I guess you can call it your time final minus your time initial. Alright? Alright? So that's pretty much, you're going to see problems I would assume, in your courses and when you're working with them, this is pretty much what you're going to see. And you can easily calculate this slew rate. And what the slew rate then is used to determine is if it can meet the needs of your application, to make sure that the amplifier can respond fast enough for the frequencies that you're going to be using at your inputs. Alright? So there you go, and that is your slew rate calculation. Alright everybody, I will see you soon.